Hello all, welcome to the video describing the current distribution in thin linear antennas. In order to illustrate the creation of the current distribution on a linear dipole and its subsequent radiation, let us first begin with the geometry of a lossless two-wire transmission line as shown in the figure. The moment of the charges creates a traveling wave current of magnitude I naught by 2 along each of the wires. When the current arrives at the end of each of the wires, it undergoes a complete reflection, which equals the magnitude and 180 degrees phase reversion. The reflected traveling wave, when combined with the incident traveling wave, forms in each wire a pure standing wave pattern of sinusoidal form as shown in the figure. The current in each wire undergoes a 180 degrees phase reversal between adjoining half cycles. This is indicated in this figure by the reversal of the arrow direction. Radiation from each wire individually occurs because of the time varying nature of the current and the termination of the wire. For the two wire balanced, that is symmetrical transmission line, the current in a half cycle of one wire is of the same magnitude but 180 degrees out of phase from that in the corresponding half cycle of the other wire. If in addition the spacing between the two wires is very small, that is spacing s far less than one wavelength, the fields radiated by the current of each wire are essentially cancelled by those of the other because the transmission lines are very near and currents are out of phase. The net result is an almost ideal non-radiating transmission line. As a section of the transmission line between 0 and L by 2 begins to flare, that is bend, as shown in the figure B, it can be assumed that the current distribution is essentially unaltered in form in each of the wires. However, because the two wires of the flared section are not necessarily close to each other, the fields radiated by one do not necessarily cancel those of the other. Therefore, ideally, there is a net radiation by the transmission line system. Finally, the flared section of the transmission line can take the form shown in the figure C. This is the geometry of the widely used dipole antenna. If L is less than the wavelength, the phase of the current standing wave pattern in each arm is the same throughout its length. In addition, spatially it is oriented in the same direction as that of the other arm, as shown in the figure. Thus, the fields radiated by the two arms of a dipole, that is the vertical parts of a flared transmission line, will primarily reinforce each other toward most directions of the observations. We are going to observe the current distribution of the dipole antenna of various lengths. The different lengths are L far less than wavelength, L equal to half wavelength. The length is varying between half wavelength and one wavelength, and the length varying between one complete wavelength and 1.5 wavelength. Here the current distribution follows the sinusoidal pattern supported by the mathematical form of sin k L by 2 for one arm of the dipole, and the pattern is symmetrical with respect to the center of the arm, where k is a propagation constant given by 2 pi by lambda and L representing the length of the antenna. Current distributions on various lengths of dipole are well simulated using MATLAB. The distributions simulated are for one arm of the dipole. Symmetry is understood for the other arm. This short code is written for a short dipole where the length is L far less than one wavelength. So, sin of KL by 2 approximately equal to KL by 2, where K is a propagation factor, 2 pi by lambda, and L is the length of the dipole. And the triangular distribution is obtained after the execution of this code. Now let's see the second code. The second code is written for a dipole of half wavelength, and the sinusoidal distribution over half wavelength is obtained, that you can see in this simulated result. Now let's see the third code. The third code is written for a dipole of one wavelength, and the sinusoidal distribution over one complete wavelength is obtained in the simulation result that you can see here. And the fourth code is written for a dipole of 1.5 wavelength that you can see here as 1.5, and the sinusoidal distribution over 1.5 wavelength is obtained like this. And you can compare the four different lengths what we have seen for a short dipole, for a half wavelength, for one complete wavelength, and 1.5 wavelength that you can see here as a collage. You can see the difference in the current distributions over the length of the arm of a transmission line. Now you can correlate the MATLAB simulation with the figures shown here for various lengths of dipole. The current pattern of very small dipole, usually lambda by 50 and lambda by 10 variation, can be approximately by a triangular distribution, since sine of KL by 2 approximately equal to KL by 2, where KL by 2 is very small. So this is illustrated in this figure. Because of its cyclical spatial variations, the current standing wave pattern of a dipole longer than one wavelength, that is L greater than lambda, undergoes 180 degrees phase reversals between adjoining half cycles. Therefore, the current in all parts of the dipole does not have the same phase. This is demonstrated graphically in figure D. For lambda, that is the length varying between lambda and 3 lambda by 2. In turn, the fields radiated by some parts of the dipole will not reinforce those of the others. The current distribution for the dipoles with L equal to lambda by 2, lambda by 4, 1 wavelength, and 1.5 wavelength and 2 wavelengths is shown in this figure. The current distribution on a half wavelength dipole is shown at different times by considering the sinusoidal nature of the currents. The distribution of currents has been assumed for the given sinusoidal function I as I naught into cos omega naught t, with omega naught is 2 pi by t. The different time instants can be substituted in the sinusoidal function. This is how the current distributions over linear dipoles is explained. This animation illustrates the effect of electrical length on the radiation characteristics of a thin linear dipole antenna. This starting at 0.33 lambda, the current distribution is concentrated near the center, producing a broad donut-shaped radiation pattern with maximum radiation perpendicular to the antenna axis. As the length increases to half a wavelength and beyond, the current distribution extends along the conductor while maintaining standing wave behavior. The radiation pattern becomes more directional and the beamwidth begins to decrease. At approximately 2 wavelengths, multiple current loops appear along the antenna. This results in the formation of additional radiation lobes and nulls due to constructive and destructive interference of the radiated fields. As the electrical length increases further, the number of current maxima and minima continues to grow. Correspondingly, the three-dimensional radiation pattern develops multiple narrow lobes with sharper nulls. Near 5 wavelengths, the antenna exhibits a highly directional multi-lobed radiation pattern, demonstrating increased directivity compared to the short dipoles. This visualization clearly shows how the current distribution along a dipole determines its radiation characteristics and how increasing the electrical length transforms the radiation pattern from a simple broadside structure into a complex multi-lobed field distribution. Thank you all and have a happy learning.